Hi class, welcome back. This is our third lesson on forces. This is our last lesson on forces. The first video lecture we learned about Newton's first law, which is basically what happens when there's no forces acting on an object. Um, our second video lecture we learned about Newton's second law, which was basically what happens when there is unbalanced forces acting on an object. And for our third video lecture, we are going to be learning about Newton's third law. And we will also be talking about the fundamental forces of the universe. And this video will also contain a good amount of practice problems. So if you struggled a bit with the concept check for last unit, this would be a helpful video as well. Before we jump into Newton's third law, we will start with a warm-up problem. A student pulls on a rope attached to a box of books, so mass of 35 kilograms, and moves the box down the hall. The student pulls with a force of 185 newtons at an angle of 25 degrees above the horizontal. The coefficient of kinetic friction between the box and the floor is 0.27. Find the acceleration of the box. So go ahead, pause the screen here. You would want to start this problem by applying Newton's second law to the forces in the x and y direction after, of course, drawing a free body diagram. So we have our crate or our box of books. We have a gravitational force pulling down on it. We have a normal force pushing up on it. Right, this thing is moving horizontally, but the person is pulling, so there's an applied force at some angle of 25 degrees. And then we know that there's friction opposing the motion as well. So we should break up the applied force into its x and y components. So we have the x component of our applied force, and then we have the y component of our applied force. And if we want to apply Newton's second law to the forces in the x and y direction, which is sort of our next step here, we can see that there are 2 x forces. So the sum of the forces in the x is equal to friction plus the applied force, and that equals max. And the sum of the forces in the y direction is equal to normal plus the y component of applied force plus the gravitational force, and that equals may. Now, I'm going to list out my notes as well. So we have the mass is 35 kilograms, which actually means that the force gravity, which is mg, is going to be 35 times negative 9.81. Which is negative 343 newtons. The applied force is 185 newtons, which means that the x component of the applied force would be 185 cosine of 25, and the y component of the applied force is 185 sine of 25. So we have 168 newtons and 78 newtons. Now mu, the coefficient of kinetic friction, is 0.27. And this is useful when it comes to solving for the force friction, right? Because the force friction would be normal times mu. And actually they're magnitudes, so I don't have my vector notation on top. All right, so my first question says, my only question says find the acceleration of the box. So the acceleration is in the x direction, right? Because the y acceleration is 0. So I'm going to need to use this equation to solve for x acceleration. So friction is unknown right now. I need to find my normal in order to find friction. So I have one unknown. This should say the x component of my applied force. Whoops, I hope you caught that. And then, so that's known. That's known. So actually, in this equation I have 2 unknowns, friction and acceleration. So I should use this equation here to solve for normal, and then this equation to find friction, and then plug it in here to find the acceleration. So my normal force is equal to may minus the y component of my applied force minus my force gravity. Right? This is this equation where I isolated Fn by subtracting these two terms. So my mass is 35 times 0, right, because it's not moving up or down, minus the y component of my applied force is 78 newtons, minus my gravitational force is negative 343. So I have 343 minus 78 gives me 265 newtons. That's my normal force. So now I can find my force friction by taking 265 newtons and multiplying it by mu, my coefficient of kinetic friction, which is 0.27. So I get 71.55 or 72 newtons as my force friction. And this thing, force friction, is pointed left. So this is going to be negative, right? And it didn't end up with a negative sign because mu is a ratio of their magnitude. So this equation here doesn't give me the vector form. So that's why I added a negative sign, because I see that it's left. Okay, I'm not done. My last step is to find the acceleration. So now I have my force friction is negative 72. My x component, my applied force is 168, right? That's that value right there. My mass is 35, and so that's my only unknown. So let me go ahead and just rewrite this down here. So I have the sum of the forces in the x equals friction plus the x component of my applied force, and that equals max. And I'm going to isolate A here. So I'm going to do that by dividing everything by M. So now I have the acceleration in the x direction equals negative 72 plus the x component of my applied force is 168. And I'm dividing that by 35. I get 2.74 meters per second squared as my acceleration. If you want to answer with 2 sig figs, you'd say 2.7 meters per second squared. All right, we are actually going to do a second problem. And this is a nice problem because we will be looking at a situation, and you'll realize this when you draw the free body diagram, but where we want to pick a coordinate system where the ground is not the x direction. So when you try this problem and you write out a free body diagram, I would like you to place the situation along a coordinate system where the displacement is on the x-axis. And you know that what I'm asking you to do might sound a little confusing before you draw a free body diagram. So if you get stuck during this problem and you need to, abandon ship partway through even part A, then you can just watch and follow along. That might even be a better idea as you see something that's a little bit more challenging than things we've seen before. A 25 kilogram crate rests on a 35-degree ramp. A worker pushes the crate up the ramp with a force of 220 newtons. The coefficient of kinetic friction between the crate and the ramp is 0.15. What is the normal force acting on the crate? What is the force of friction acting on the crate? And what is the acceleration of the crate? Go ahead and pause here. And again, if you need to kind of abandon ship and just watch this video first, that is totally fine. There's going to be a question like this on the problem set where you are adjusting a coordinate system that's not necessarily what the traditional system you would use, where you have ground as the x, but you'd use one that's a little bit easier. All right, we have a 25 kilogram crate resting on a 35-degree inclined ramp. So there's my 35 degrees. And we have my box right here. And a worker is pushing the crate up the ramp. So here is an applied force. And that's 220 newtons. And I also have a force of gravity acting on this thing, pointed down. I have a normal force that's perpendicular to the surface. And I have friction pointed opposite the direction. So, this free body diagram here shows me how I really can't, well, it's not that I can't. I don't want to use an coordinate system where the y or the x direction lines up with the ground, right? Because then I would have so many vectors that need to be broken up into their different components. So instead, what I'm going to do is I'm going to take this free body diagram, I'm going to shift it and stick it on a coordinate system where the applied force and friction are along the x direction, opposite directions, and normals pointed up on the y. So I would have something that looks like this. Here's my y, here's my x. I would have my normal force pointed up. I would have my force friction pointed to the right. I have my force applied pointed to the left. And now I have my force gravity pointed like this. So now I have an x and y component for my force gravity. So if this angle is 35 degrees, then this angle is 35 degrees, which means that this angle right here, which is the one we want to use the angle down from east. It's not that we have to use that, but if we want cosine to go with the x component, then we need to use the angle theta down from east. So that is going to be 55 degrees, right? 90 minus 35. And I'm going to break up my force gravity into its x and y components. So the x component of gravity is going to be mass times acceleration due to gravity times the cosine of 55, which will be, and I shouldn't have done that so close, that's going to be 25 times 9.81 times the cosine of 55. And I got 141 newtons. And my x component of gravity points in the positive direction, so I'm going to keep that as positive. That's why I didn't put my negative sign here. But if I did, right, if I put negative and then end up with negative, I would just look at my diagram and say, actually, you know what? I'm pointing to the right for my x component of gravity, right? My x component of gravity is going to be rightward, so this would be a positive 141. Now, the y component of my force gravity is going to be mg sine of 55. So that's going to be 25 times negative 9.81 times the sine of 55, which is negative 201 newtons. And my y component of gravity is pointed down, right? That's my y component. So it should be negative. So now I have my x and y components, which will be useful when I go ahead and solve for different quantities. So my question is asking me to find the normal force. Let's zoom out a little here. So I'm going to sum together the forces in the y direction because that's the direction that would have normal. So the sum of the forces in the y is normal and then y component of gravity. And that equals MAY. Now, this object's not moving in the y direction, right? The displacement is along the x now. So I can solve for the normal by taking MAY minus the y component of gravity. And that would be 25 times 0 minus my y component of gravity is negative 201. So my force normal is 201 newtons up. Next part of my question says, what is the friction force acting on the crate? So I'm going to sum together the forces in the x because friction here acts in the x. And I have friction pointed right. You may have drawn your diagram where it's pointed left. It doesn't really matter. You'll get the same answer. So the sum of the forces in the x equals friction plus the applied force plus my x component of gravity. Don't forget the x component of gravity, right? That's really important here. So that will be, oh, that's equal to MAX. So I'm looking for the force of friction. So my force of friction is equal to MAX minus my applied force plus the force gravity in the X. And as I'm writing this out, I'm thinking, man, I must have more than one unknown here, right? This is an unknown. My X acceleration is also unknown. So I can't actually use this equation. So let me just revisit my initial question. It says that I have a coefficient of kinetic friction. Okay, that's useful, right? Because the coefficient of kinetic friction multiplied by my normal gives me my force friction. So I can use this equation to solve for force friction. So I have 0.15 times my normal force was 201. And that gives me 30.15 or 30 newtons. And for me, on my diagram, I have friction pointed right. So that 30 newtons is positive is fine. If yours is pointed the other way and you got negative, that's okay too. All right. Now I'm on to my last problem, which is part C, finding the acceleration. So let me go back to this equation here, and I will isolate the acceleration. So the acceleration in the x direction is equal to friction plus the applied force plus the x component of gravity, and that's all divided by the mass. So friction for me was positive 30 newtons plus my applied force is 220 newtons, but it's actually negative for me. It's pointed left. So I have negative 220, and then the x component of gravity is 141. And I'm dividing that all by my mass, which is 25. So 30 minus 220 plus 141 divided by 25, I got negative 1.96 meters per second squared, which, if we're looking at two sig figs here, we can say it's 2.0 meters per second squared to the left. It's actually up. So, you know, I got a negative sign. Negative sign usually indicates left or right. It's really 2 meters per second squared at an angle of 35 degrees, right, up from east. Okay, so on to Newton's third law. For every force, there is an equal and opposite force. You know, I worded Newton's third law in a way that is sort of a hat tip to what you may have heard in middle school, which is for every action, there's an equal and opposite reaction. And it's not that that phrase is wrong, but the point of Newton's third law is that forces come in pairs. If you push on an object pushes back on you, and the magnitude of those forces are equal and the direction are opposite. And that's really what Newton's third law is. This explanation I have written here in the slide uses the phrase action and reaction, which is sort of misleading because it's not that there's one force that initiates the second force. And when you use words like action, reaction, it sort of implies that there's an initiation process, right? Like I hit the wall and then the wall hits me. But that's not really what happens. When I hit the wall hits me at the exact same time. It's not really an action, reaction. It's sort of both forces acting at the very same moment. So a better way to think about Newton's third law is to say that forces come in pairs. And this is always true. There is no singular force. Now, when we look at free body diagrams, we are always drawing the forces that are acting on one specific object. So you don't see those pairs on a free body diagram, right? Like if you were to draw a diagram of me right now sitting in this chair, you would have the force of gravity pulling down on me and the normal force pushing up on me. You don't see either of those pairs on the diagram because it's just of me. But if you were to diagram the Earth, you would see that I'm pulling up on the Earth. So there is a force from my mass that is pulling up on the Earth, right? And likewise, as I push down on the chair and the chair pushes up on me, that's a pair, one of these Newton's third law pairs. But when I'm diagramming just me, you only see the force acting on me, not the one acting on the chair. So it's true that all forces come in pairs. In free body diagrams, we're only looking at the external forces that are happening on one specific object. So let's say you're driving down the road and a firefly strikes the windshield of a bus. This is a case of Newton's third law of motion. The firefly hit the bus and the bus hits the firefly. Which of these two forces is greater, the force of the firefly or the force on the bus? Well, I hope you realize that the answer to this is that the forces are equal. The firefly, however, experiences a much greater acceleration or change in velocity than the bus does because the bus has a really, really big mass compared to the bug. So if net force equals mass times acceleration, then and we say, okay, well, the force from the bus onto the bug is equal to the force from the bug onto the bus, and the bug experienced a large acceleration, it's because it had a small mass, whereas the bus, which has a large mass, experiences a small acceleration. All right, so we know that the Earth pulls on the moon, right? Because the moon is in orbit around the Earth. And, well, we'll talk about gravity and we'll talk about orbit next unit, but actually not next unit, our last unit. But we do know that the Earth pulls on the moon because the moon's in orbit around the Earth. But do we know whether or not the moon pulls on the Earth? And I hope you realize now that the answer is yes, because forces are always going to come in pairs. They pull on each other. So if I asked you which is stronger, you would hopefully say they're the same strength, equal in magnitude, opposite in direction. Now, I'm remembering back to our first slide, and I'm not sure that we had this piece on there. So if you're taking notes, then I'd ask you to add this last piece. If you're not taking notes, which is totally fine, because I give you guys a printout of the notes or like a handout of the notes at the end of the list of assignments for the week. This information's in there already, but I keep mentioning that the forces that objects exert on each other are equal in magnitude, opposite in direction. So that is something we should have under definition of Newton's third law. All right, sorry for the interruption. Back to our problem on the Earth and the Moon. So the Earth exerts a gravitational force into the Moon exerts a gravitational force into the Earth, and they are equal in magnitude and opposite in direction. And if I asked you for some evidence that the moon really does pull on the Earth, you might tell me that some evidence of this phenomenon is tides, right? The ocean tides ebb and flow because of the gravitational field around the moon. So the Earth and the moon exert gravitational forces on each other. The moon's gravity pulls on the Earth, which causes the water in the oceans on Earth to bulge out towards the moon, and that creates what we call high tide. Now, at the same time, on the opposite side of the Earth, there's another high tide because the Earth itself is being pulled slightly towards the moon, which leaves the water behind, right? So that's what this and this bulge are here. So the gravitational pull from the moon creates two high tides on opposite sides of the Earth. However, the gravitational pull of the sun also affects the tides, but its effect is weaker because it's very far away compared to the distance between the moon and the Earth. When the sun, the Earth, and the moon are aligned, though, during the new moon or the full moon phase, the gravitational forces of both the sun and the moon combine, which leads to the spring tides. Those tides, spring tides, are higher than normal. That's why you see really big tides during those phases. But on the other hand, when the moon is at its first or third quarter phase, the sun and the moon pull at right angles to each other, which results in neap tides, where the difference between the high tide and low tide is much smaller. So, anyways, I'm kind of going into a lot of detail here about tides, and it's not necessarily super important for our study, but it is interesting, and it does, you know, have to do with the fact that the Earth, the Moon, and the Sun are all pulling on each other. Okay, let's try a problem with Newton's third law. Superman stands with a mass of 67.5 kilograms and saves the Earth by moving an asteroid which has a mass of 7.33 times 10 to the 6 kilograms. The asteroid starts at rest but is accelerated to 9.34 meters per second in the 6.6 seconds it takes Superman to push the asteroid away. How fast is Superman traveling after the push? This problem is going to require kinematics, Newton's second law, and Newton's third law. So go ahead and pause the screen and give it a go. All right, so we have a situation where Superman, let me write this down. The mass of Superman is 67.5 kilograms and saves the Earth by moving an asteroid. So the mass of the asteroid is 7.33 times 10 to the 6 kilograms. The asteroid starts at rest. So the initial velocity of the asteroid is 0, but it's accelerated to, so final velocity of the asteroid, 9.34 meters per second in the 6.6 seconds that it takes Superman to push it away. So, the asteroid was coming towards Superman, and then he stopped it and then pushes it away. So we're looking at the interaction after it comes to rest, and he's pushing it away. So let's find the final velocity of Superman. Now, first of all, we need, right, if we want to find the final velocity of Superman, we know the initial velocity of Superman is going to be 0 because, the asteroid comes to Superman, it pushes him back, they come to rest, and then he pushes off of it, and it, the conservation of linear momentum would say that, Superman gets pushed backwards when he pushes the asteroid forward. So, anyways, my initial velocity of Superman is 0. I'm looking for the final velocity. I know the time frame of that interaction, 6.6 seconds, but that's it. I know these are the only two things I know in terms of kinematics quantities for Superman. But what I can do is I can use this information for the asteroid to solve for the acceleration of the asteroid. And then I can use Newton's second law, F equals ma, to find the acceleration of Superman. And that would be my third kinematics quantity. So let me write that down. And this is a hard problem, so maybe it would be helpful if I actually write the steps down and then give you the opportunity to pause the video again. So 1, find the acceleration of the asteroid. And you would do that by using these kinematics quantities for the asteroid. 2, find the force from Superman onto the asteroid and from the asteroid onto Superman. They're equal in magnitude, opposite direction. And remember, F equals ma. 3rd, find the final velocity of Superman using kinematics. All right. So the acceleration of the asteroid is going to be found by using initial velocity, final velocity, time, and acceleration. And that equation is v final equals v initial plus a delta t, which means that a equals v final minus v initial over delta t. So v final is 9.34 minus 0 over 6.6. That's 1.4 meters per second squared. That is the acceleration of the asteroid. Now, the force from Superman onto the asteroid is going to be the mass of the asteroid times the acceleration of the asteroid. So the mass of the asteroid is 7.33 times 10 to the 6th kilograms. And the acceleration of the asteroid is 1.4. So the force from Superman onto the asteroid is 1.03 times 10 to the 7th newtons. Now, the force from the asteroid onto Superman is going to be negative 1.03 times 10 to the 7th newtons, right? Equal magnitude, opposite in direction. And I guess there's a 2.5 step, or really a step 3 and then a step 4. But I need to find the acceleration of Superman from this. So the acceleration of Superman is going to be equal to the force of Superman, or on Superman, divided by the mass of Superman. So that will be negative 1.03 times 10 to the 7th divided by 67.5. So the acceleration of Superman is 1.5 times 10 to the 5th meters per second squared. Now the initial velocity of Superman is 0. The time that they're in contact is 6.6 seconds. So I have 1, 2, 3 knowns. I'm looking for final velocity. So I'm going to use the equation V final because V initial plus A delta T. So V final is equal to 0 plus my acceleration is 1.5 times 10 to the 5th times 6.6. And that gives me 1, 2, 3, 4, 5, 6. 1.0 times 10 to the 6th meters per second. So the last piece of this lesson today will be on the fundamental forces of the universe. So all of the forces that we've talked about today, all the forces that we talked about this unit, right, like friction and buoyancy and thrust and normal and drag and weight and tension, all of these forces, they can all be reduced into one of the 4 fundamental forces. And what I mean by that is that those mechanical forces that we learned are really just different manifestations of the same fundamental force, right? Like, for instance, weight is caused by gravity. So, weight is not a unique force. It's really the gravitational force. The normal force is caused by the electromagnetic repulsion between atoms. So the normal force is not its own unique force, right? It's actually a manifestation of what is called the electromagnetic force. Friction is caused by the electromagnetic interactions between microscopic surface irregularities and just the electrons in the outermost portion of the atoms. And so friction is really a manifestation of the electromagnetic force as well. Tension, too, is caused by electromagnetic forces that are holding atoms that are in a rope together, or a cable or a string or whatever. So actually, a lot of the macroscopic forces that we deal with on a day-to-day basis are really the electromagnetic forces. And gravity and the electromagnetic force are both field forces. And actually, all of the 4 fundamental forces of the universe are, in fact, field forces. There are no real contact forces because nothing on a molecular level is really in contact with each other in the way that we think about it when we first introduce these concepts. So the fundamental forces of the universe are the electromagnetic force, which I just explained a little bit. This has to do with the behavior of charged particles, the interactions they have with each other. There is the gravitational force, which is that force of attraction between all objects in the universe, all particles in the universe. There's the strong nuclear force and the weak nuclear force, which have to do with the subatomic interactions that happen within an atom. So the strong nuclear force is the force responsible for holding the nucleus of an atom together, and the weak nuclear force has to do with particle decay and radioactivity and things like that. The gravitational force is the weakest force, and the strong nuclear and the weak nuclear act on a level that's inside the atom. So on our day-to-day, macroscopic world, we're usually dealing with the electromagnetic or the gravitational force. So as we continue studying physics, we see that these different phenomenon that we talk about, right, like the things that we talked about mechanics so far, are actually connected by a really small number of fundamental principles. And this process of simplifying things is one of the central goals of physics. So in terms of modern day physics, we have a lot of worldwide efforts going on at places like the Large Hadron Collider at CERN, which is a lab on the border of France and Switzerland. There's a particle accelerator where we send, the most brilliant people that are alive today, right? They work at this particle accelerator. And what they're doing is they're trying to mimic the conditions of the Big Bang, and they're trying to create really, really, really high energy situations and see what happens when you slam particles together. And what we found through experiments is that the electromagnetic force and the weak nuclear force are actually connected in really, really high energy situations. They come from the same force, which is called the electroweak force. And there is a theory that the electroweak force and the strong nuclear force are actually connected in a single framework known as the grand unified theory. So we have mathematical models for the grand unified theory, but we have not actually experimentally confirmed anything. And so really what that leaves out of our understanding is the gravitational force. And so there is this idea in modern physics that gravity is actually connected to the grand unified theory through something called the theory of everything that would connect all four of these fundamental forces into one principle that governs everything in the universe. So this course that you're taking right now focuses on classical mechanics, and it might seem far from the situation in modern physics that I'm talking about right now, but it's really not, because the principles that we learn here form the foundation for deeper ideas. And every branch of physics, right, from quantum mechanics to cosmology, they build upon the concepts of force, motion, and conservation of energy that begin with Newton's laws. So I hope as you continue on in the study, you can sort of think about how these fundamental principles that we're learning really form the basis of this much broader understanding of how the universe works as a whole. Thank you all for tuning in to today's lesson. I hope that that little tiny bit of information I gave you guys about the fundamental forces of our universe kind of showed you a little bit about why so many people are fascinated with the study of physics. It really is a very beautifully simple field, and it's pretty interesting that the more you study it and the deeper you get, the more you realize how simple it truly is. And that's very attractive to a lot of people. The feeling of connectedness that you feel with the universe when you study these things on a deep level is really powerful. And I think it's what draws so many folks to particle physics and a lot of these modern physics fields. So, anywho, I will see you next week.